Welcome to the virtual field excursion, which we're going to try and make as close to the actual excursion as we can by way of this film. Here we are standing at the mouth of the Hunter River, which was the main entry into the coal producing areas to feed the early colony of Sydney with coal. Ships previously could travel straight through the heads here, the island of Nobbies over in the distance, and into the river. It was a very dangerous entry, and Governor Macquarie decided to use convict labour to build a pier or a breakwater, and he used the Waratah sandstone. Now, when I talk about the Waratah sandstone, I'm referring to a name of a sequence which underlies the rocks which we're going to see today. We refer to that as the stratigraphy. The stratigraphy is simply the layering of the oldest rocks at the bottom and the younger rocks upwards. I'm going to use a number of terms today, and in the notes you'll see that there is a list of terms which you should know, and if you don't understand terms that I use today and I haven't explained them, then you really need to get to know those terms using your dictionary. In your notes you will find a map, and the map will indicate the points at which we stop. There's also a grid, and in the notes there's a way of working out your location using a grid reference, a six-figure grid reference. So each of the points we stop at, you can identify and then locate them using the grid reference. When this pier was built, it actually blocked off the way in which the water could flow. So the beach that we have here is an artificial beach. It's produced by longshore drift. The southeasterly winds blowing up the coast drags the sand up and deposits it. So if you put a blockage in the way, it will create an artificial beach. Before we move on to our first stop, I refer you to the stratigraphy in your notes, and that is the sequence of rocks which we will be identifying and looking at today. So we will now start our excursion by walking up towards Nobbies, which was an island but is now linked to the mainland through Governor Macquarie's pier. Here we have blocks of the Waratah sandstone which were used initially to build the first pier of 1818. I'm hoping we can actually send you a sample of this to examine, but what you'll notice here is that these blocks are not in place. So any measurements of dip or strike would be meaningless. What they do show is that they are very easily weathered. We can easily break pieces off and we can feel them to get an indication of the coarseness of the grains. It's probably about the same size as salt, fine-grained and easily broken apart, crumbling into your hands. The type of weathering that we see here is called honeycomb or snuffbox weathering. It's produced always in areas such as this at the coast or in the desert. Why do you think that might be? What are the common factors? One of the common factors is that wind carrying salt is abundant in both areas, and what happens is salt-laden wind brings in water and salt together. The salt crystallizes as the water evaporates, and as it crystallizes, it tends to break apart the grains, these fine grains of sand. The wind then, carrying wind-blown sand, will break up the softer bits where the salt has broken them up, and that leads to this particular feature which we call honeycomb or snuffbox weathering. And here we have another block of Waratah sandstone. Once again, it's not in place, so any measurements of the direction of strike or the dip of these beds would be meaningless. What it does show, however, is the very fine-grained nature of the sand that was deposited to produce the rock. It shows the bedding itself, which you can measure if it was in place and give you some information about the rock. These surfaces here are the bedding planes. Each of the beds is separated by a bedding plane. It also shows the typical snuffbox weathering, And in this line here you can actually see little ripple marks which help us tell, if it was in place, which way up the rock would be. So from this we can interpret that we have a very even-grained, very finely layered rock, which suggests that the deposit, which is probably a river deposit, was very slow flowing, very even velocity, and produced ripple marks or very fine layers as the material was laid down. It also demonstrates how easily weathered this rock is. You can see how it's breaking up at all of these points, very easily weathered. Here we have another block of Waratah sandstone which shows a few more features. The first one to notice is it still has this very fine sedimentary layering or bedding. We have bedding planes exposed on some surfaces. These are the fine bands. On this particular one we have little ripple marks, very clearly defined. Over here, which might be difficult to see, we have cross bedding. In other words, the water has come in this direction and deposited on a sloping surface which is not parallel to the bedding. This sloping surface is always concave downwards in the direction of flow, so you can tell whether the rock is the right way up or upside down. This is known as cross bedding. The beds slope upwards and then are cut off very sharply by the next horizon. One other feature to notice in here is these surfaces here, which are also very planar. Those are joint surfaces. What's the difference between a joint and a fault? There's no difference really, excepting that a fault has had relative movement on either side, whereas a joint has no movement associated with it. And here we have a completely different type of rock to the Waratah sandstone. What do you notice about this rock? The first thing is that it's not as weathered. It doesn't crumble as easily. So if I hit it, it doesn't break. It's a much harder rock. This rock is brought in to protect the pier against erosion by waves. It's a much harder rock, and it also hasn't got that same layering in it. You'll notice it doesn't have the bedding planes. It is simply massive. What else do you notice about it? Have a look at it, and you'll notice it has small crystals in it. And the crystals are in a much darker matrix or ground mass. We prefer to use ground mass for igneous rocks. The fact that it's got crystals would suggest its origin is not the same as the sandstone, but in fact is an igneous rock. This rock is in fact a dacite, which is an intermediate rock containing quartz, plagioclase and orthoclase. Orthoclase, from your mineralogy you will remember, is one of the feldspar group, and it has a cleavage. That cleavage allows it to reflect the sunlight, so it sparkles. The other feature you'll notice is it has two sizes of crystals. It has the coarse crystals, or relatively coarse crystals, and you can measure those on the samples that I send you, and the very fine-grained material in which they sit. What does that tell us about the history of the rock? It tells us there have been two periods of cooling. One relatively slow, when the crystals could grow, and then one relatively fast, which effectively produces the ground mass fine crystalline background. The answer to the question is, well, the history of the rock is that it is essentially a volcanic rock which has crystallized the bigger crystals, quartz and feldspar, at depth, then erupted, and a very rapid cooling to trap those crystals in the finer grained ground mass. Well, what do we have here? We have a completely different sort of rock type. It's on the pier. It's also used as an armor stone. They call it armor stone because it armors or protects the pier against weathering. This rock is different in the sense that it is much heavier, which is good for armor stone because it's not moved by the waves. Its disadvantage is that it tends to break down by weathering, just as the dike in Nobby's Tuff, which we'll see. It hasn't got those big crystals in it. It's very fine grained, very even grained. This is also an igneous rock, and this is a basalt. When this weathers, it weathers to a rusty brown colour. I have looked for some to show you, but unfortunately they've covered all the weathered ones with new deposits of armour stone to protect the pier. So you'll just have to take my word for it that when this basalt weathers, it produces a reddish brown weathering surface. Here we are at Nobby's Headland, which used to be an island before they built the pier. It used to be another third higher than it currently is, but they removed the top third because they wanted the wind to help the ships get through, because in those days they depended on sail. At the very top, the bit that's been removed was the conglomerate, and if you look at your stratigraphy you'll see that was the Merriweather conglomerate. Immediately beneath that is a dark greyish shale, and immediately above that is a thin layer of coal. That's the Victoria Tunnel coal seam. Underlying that we have what looks like a banded sequence of rocks. Those rocks represent the Nobby's tuff. Tuff, T-U-F-F. It's a volcanic rock, a volcanogenic sediment. Around about 220 million years ago, there were very major volcanic eruptions offshore. Not the present shore, because it didn't exist then, but the old shore of the Permian. And those eruptions poured out large volumes of ash, and the ash settled down. The first layer to settle would become fused and hard, and there's a sample of that. The next layer, which would have settled more slowly, produces a shaly horizon. And if you look at the edges, you'll see that the shaly horizons are weathered more readily than the more consolidated horizons. They are both tuff. At the bottom of the sequence, covered by the sand, is another coal seam, and that is the Nobby's coal seam. So now you have the stratigraphy represented by this one cliff face. Cutting through the whole sequence is another rock, a vertically intrusive dike. That weathers differently. Near the top, it weathers into the horizon. Near the bottom, it sticks out, it protrudes. The reason for that is near the top, you have chemical weathering predominant. Near the bottom, where you have sandblasting and wave action, you have physical weathering predominant. And that rock type, which is a very weathered basalt or dolerite dike, represents a single rock type which is weathered slightly different. It cuts across the tuff, so it's much younger. It's actually dated from about the time when New Zealand and Australia separated about 60 million years ago. If you look at the jointing in those rocks, the joint spacing in the more consolidated tuff is actually quite widely spaced. In the finer shaly horizon, it's narrow, which allows the percolation of groundwater both horizontally in the shaly beds and also vertically through the frequent jointing. In this area, you're asked to draw a sketch. There is an example of a really good field sketch, so try and use the information you have from this virtual field trip to draw your own sketch, not forgetting a scale. If you look at the edge over there, you'll see that the rocks go in and out. That's differential weathering, and it's because those shaly horizons weather more readily than the coarse horizons. The last thing to think about is how high is that? It's about 30 meters high. From the bottom of the Victoria Tunnel coal seam to the beginning of the Nobby's coal seam, which you can't see, but let's call it the sand level, is about 30 meters. And that's important as we move down the coast, because you'll see that the bottom of the Nobby's tuff, which here is at sea level, does not stay at sea level all of the time. Just remember, the top was the Merriweather conglomerate, which has now been removed. We've had a look at this general cutting, which is an artificial cutting, and it's exposed these rocks, and they have produced a very unusual appearance, this rather pitted looking appearance, which is the first thing to attract your eye. However, it is something which is superficial and shouldn't be looked at seriously. What we really want to look at is the material within. The reason this pitting occurs is because the rock is so friable. It's just like loose sand, and only small parts of it are resistant to the weathering. If we look through the weathering, what do we see? We see rounded pebbles which may be supported by themselves, which we call clast supported because the rounded pebbles are clasts, or they may be supported, as we see in some areas, by this loose friable sandstone. So in fact it is then matrix supported. So they can either be matrix supported or clast supported. Where do we get rounded pebbles from, and what does it produce? Well, rounded pebbles, which are either clast or matrix supported, are in fact forming a conglomerate. And what we have here is the Merriweather conglomerate, which we previously would have encountered on the top of Nobby's Tuff if it hadn't been removed by the engineers. If we want to look more closely at this, we see different features. One of them is this broad curved feature here, which has a base of rounded pebbles grading upwards into sandstone. This is graded bedding. Graded because the heavier, bigger material is at the bottom, the finer, looser material is at the top. In addition, remember we're looking at this in 2 dimensions. If a river is flowing in this direction, what would we see? We'll see the bed of the river or the channel as if it was an upturned shield or an upturned U-shape. This is what we're seeing here. So this is a river channel where the deposits have been on the base, cutting in over a previously deposited sandy horizon. So we've got graded bedding and a river channel. And if we look further, more closely, we can see here a river channel which is cutting off a previously deposited layer, as in cross bedding. So we have graded bedding, cross bedding, river channels. Where might this material have come from? First of all, because it's a conglomerate, it would have required reasonably high velocity of water to carry the pebbles and deposit them. And also then, of course, to suddenly or gradually reduce the volume of water so that the energy level dropped and you could then deposit the conglomerate. At the time this conglomerate, this Merriweather conglomerate, was deposited, the New England belt was impacting against the Sydney Basin, really along 2 major thrusts, the Hunter-Mookai thrust and the Peel thrust zone, and that was throwing up mountain ranges which had high topography, rivers flowing off them, filling up this basin to the south. So that provided us with the water and the energy to deposit the Merriweather conglomerate into the Sydney Basin. Now here's a sample that I've taken off the cliff and brought out to demonstrate more accurately the features. First of all, we have these rounded to sub-rounded pebbles, which are themselves somewhat weathered. At some point they actually supported one upon another. These are clast supported. They're the coarser ones down at the bottom. As we move upwards, they get finer and finer, smaller pebbles, and now they become matrix supported until ultimately they disappear and we only have the sandstone. So over that distance we have a graded bed from medium grain pebbles, which are sub-rounded, elongate upwards into a sandstone. This would be one bed within the horizon. So in general what we've seen then are graded beds, conglomerate beds, channels and so on. What sort of features are produced by braided rivers? Exactly these sorts of features. So braided river system has produced this conglomerate, relatively fast flowing, enough energy from the mountains, and then occasional cross-cutting previously deposited material. So if you visualize the river systems for South Island in New Zealand, for example, they would be braided rivers, rivers which cross themselves and cut into previously deposited material. I'm standing at the on a wave-cut platform on the Bar Beach Formation at the northern end of the Bar Beach car park, which you should be able to find on your maps. Behind me we have a stratigraphic sequence right at the top where there's a little black dot, which is the trig beacon. That's on Merewether conglomerate. Beneath that is a small black horizon, which is the Victoria Tunnel coal seam. Beneath that is a very, very distinctive Nobby's Tuff. And below that is another black horizon, which is the Nobby's coal seam. Now, if you remember, when we were at Nobby's, that coal seam was not visible. It was under the sand. So the base of Nobby's Tuff was at sea level. At the moment, it's probably about 60 meters above sea level. Obviously the sea hasn't changed, so what we can deduce from that is that the rocks have been folded upwards. This is known as part of the Shepherd's Hill anticline. If you imagine the New England block pushing up with two great thrusts towards the Sydney Basin, it produces minor folds within the overall basin. The rocks at the Merewether conglomerate outlook were dipping in a southerly direction down towards Sydney. This is an excellent place to look at the overall stratigraphy. At the top, the Merewether conglomerate. The next, we have the Victoria Tunnel coal seam. Below that, we have the Nobby's Tuff. Below that, we have the Nobby's coal seam. Below that, we have the Bar Beach Formation, which also forms a cliff-like feature over there. Below that, we have the Dudley coal seam, which is right at the top of where that green vegetation starts with a gentle slope downwards. That slopes down to the Bogey Hole Formation, which again forms a cliff-like feature, and what we're standing on at the moment is the Bogey Hole Formation. Behind me is a cliff in the Bogey Hole Formation, which you can see is another fine-grained sandstone, cross-bedded with the same sort of weathering features as we saw in the Waratah sandstone. Very similar type of rock, very similar conditions of deposition. We're about 400 meters south of the Merewether Baths at the base of a cliff above which is Scenic Drive, so you should be able to locate yourselves pretty well. If you look at the cliff face there, you will recognize certain of the stratigraphy that we have seen previously. You can recognize Nobby's Tuff, which is so characteristic that it's used as a marker horizon. At the base of it, hidden in the bushes there, you can just see a little bit of the Nobby's coal seam. At the top, the greyish shales, which represent the Victoria Tunnel coal seam. So Nobby's Tuff is right in the middle of that cliff. If you look at the base of it, which is the Nobby's coal seam, you'll see that that's approximately 30 meters above the wave-cut platform I'm standing on, which is about the same as sea level. So from Nobby's, where it was at sea level, when we were at Shepherd's Hill, it was about 60 meters above the sea level, and now we're down to about 30 meters. So it's demonstrating there is a broad structure. There's one other feature here, and that is if we look to the left, you'll see a little gully. If we look at the level of the coal seam on this side, on my right-hand side of the gully, you'll see that it is not at the same level as the coal seam on that side. Why would that difference be there? Well, the answer is there's a fault, a very small fault with a small displacement of about 3 or 4 meters, where the left-hand side is down-thrown relative to the right-hand side. So here we have our sequence allowing us to demonstrate not only the stratigraphy, but the broad-scale features and a fault. And that is the value of marker horizons, which we can follow over long distances. With the panoramic shot, we've effectively got a steady southward dip, which is consistent with the basin, which is dipping towards Sydney, down towards the south. However, within that, there are a number of small features which we can identify. The first one is the change in the height of the base of Nobby's Tuff. In fact, that whole sequence goes from sea level up about 60 meters and then down to about 30 meters. At this point, where we are just below Hickey Drive, the scenic drive area, we've already picked up one small fault. In this area we have flat-lying Nobby's Tuff, which is unusual because it's now lower than the rock on my left, which is again back to the normal southward dipping Nobby's Tuff. Why has this happened? Well, if you look closely, you'll see it sits in a gully. And the most likely explanation is there has been a relatively recent landslip which has dragged all of the rocks down. So on both sides we have faults which have allowed the material to slip downwards towards me, towards the ocean. I'm standing on another wave cut platform in the Bogey Hole Formation, and what I want to show you here is the semi-regular, almost rectangular pattern of joints which is developed. If it's highly regular, it's sometimes called a tessellated pavement. In this case, it's not quite that regular. Joints like this develop as a result of a release of pressure. Quite often it's simply the erosion taking away the mass of rock above it. Other times it's a function of some of the folding. These joints allow water to percolate through, and water coming down from above is quite often enriched in elements dissolved out of the sediments lying above. One of the most common is iron. As that percolates through the joints, it precipitates out the iron, which then migrates away from the joint. The iron oxide, or limonite, is slightly more resistant to weathering than the surrounding sandstone. As a result, if you look at the joints, you'll find that they have a little raised ridge on either side of the joint. Sometimes the water will flow in the horizontal joints. Horizontal joints are a function of the loss of a load of pressure above, and as a result they open up parallel to the bedding, or close to parallel to the bedding. That's where most of the iron oxide can be precipitated. And if you look around, you'll see a lot of areas with this reddish brown iron oxide precipitation, which is more resistant to the surrounding sediment, which is why you have these strange tabular looking features, or sometimes semicircular features. So the noticeable features here are the joints, which are raised as the water's percolated away and precipitated iron oxide, and the flat-lying joints in which you have a large volume of iron oxide precipitated, making them resistant to weathering. Well, this concludes the virtual field excursion. In summary, we've travelled to 5 locations along the Newcastle coastline and examined various rock types and the stratigraphic sequence of the area. You will be receiving samples of some of the rock types. To complete the activities set out in the associated assignment booklet, review sections of this video and the other provided resources. A handy tip for your sketches would be to use the video pause controls. Good luck in submitting your work.